Hi everyone. I'm recording from home today, so I would like to welcome you to my house. I have one person to introduce you to though, and it's right up there. That's my palm plant Floyd. He says hi. So now we're going to talk about Millikan's oil drop experiment. So it wasn't known at first how much charge there was on a single electron. Coulombs were used for electricity measurements, but they didn't know how much a single charge held. And so Robert Millikan and Harvey Fletcher put together this experiment in 1909 to figure out how much charge there was on one single electron. So here's the setup. This box over here is a chamber just with air inside it. On the top, right up here, we have a metal plate, and on the bottom is another metal plate. Those two metal plates were attached to a voltage source, an adjustable voltage source. Okay, so here's one wire, another wire, and they were attached to this. We're just going to make it a box with a dial on it. Okay, and so they can adjust the voltage between these two plates. Higher voltage means that they would create a greater electric field between them. And they hooked it up so that the top plate was positively charged, and the bottom plate was negatively charged. So we talked about electric fields and how to draw them in the last couple lessons. So this is what it looks like here. The field points in the direction of the force on a positive charge. Okay, so if you think about this positive plate up here, it's going to repel charges toward the negative plate, right? So our field between these two plates is going to look like this. Okay, there's more field lines. I just want to leave my central space open for some other things. Okay, so our field is pointing downward. That's going to be important. Now, in this top piece over here, this is like a perfume bulb, okay, from those old-fashioned perfume misters. Inside that bulb, he has some oil, okay, and so when he would squeeze the bulb, then a bunch of microscopic oil drops would be pushed into this upper chamber over here. Okay, so this chamber is getting filled with just an oil mist. Now, there's also a hole in the top plate right over here that will allow oil drops to fall down into the main chamber. Okay, so here's what's happening now. You've got every once in a while, a little oil drop is going to fall into the main chamber over here. Okay, so they're just going to fall down toward the bottom plate. Nothing special, it's just drops of oil falling through the air. But what made this a little bit different and what made the experiment work was that he added one more component to that central tank, that central air chamber, and it was an ionizer. So I'm going to just draw it like a gun. We're going to call it an X-ray gun. Okay, so he put together this middle chamber with an X-ray source attached to it, and so the X-ray source would fire X-rays into the main chamber and ionize the air. And so what happens with ionized air is that now there's all these free electrons that are going to be bouncing around all over the place. And so each of these drops would maybe pick up a few electrons, depending on its size, become charged. So now we're just going to zoom in on one particular drop. Okay, so now we've got, just one second. Now we've got our two plates, one plate, two plates, they're charged, and you have this drop in between them. So we're just zooming in on one of the drops. So let's say that this drop has picked up, I don't know, 3 electrons. So here's 1 electron. We're just going to represent them by negative signs. So this drop has picked up an extra 3 electrons. It's charged, and it's going to be affected by the electric field. So our electric field is pointing downward. Let me just draw that really quick. Our electric field is pointing downward. Our upper plate is positively charged. Our bottom plate is negatively charged. And so the electric force on this oil drop is going to be upward. Okay? Negative charged drop, positively charged upper plate, negatively charged lower plate. That means it's going to be pulled upward by the electric force. Okay, but this oil drop also has mass, and so it's also going to be pulled downward by the force of gravity. Okay, now because they set up this adjustable voltage source, they could adjust the charge on each of the plates, and that meant that they could also be adjusting the electric force using that thing. So their goal was to adjust the voltage, adjust the charge on these plates until the electric force and the force of gravity were equal to each other. And because they knew the density of the oil, they could calculate how much mass the oil had. So they also had a kind of microscope lens like this that had graduations on it. So what I mean by that is a little measuring device. So they could see exactly how big this oil drop was. And again, because they knew the density of it, then they could calculate its mass pretty accurately. So they knew the mass of the oil drop. They knew the acceleration of gravity was 9.8 meters per second squared. And when the force of gravity and the electric force were balanced, that would mean that the electric force would be equal to mass times 9.8. Okay, so this part over here, they could measure that, they could calculate it. This part on the left side, electric force, is also Q, let's try this again, QE, electric field strength. Okay, so this was the formula that they used. QE equals mass times 9.8. Let me just fix this a little bit. There, beautiful. Okay, and also because they were adjusting the voltage on that adjustable voltage source, they knew what the electric field strength was as well. Okay, so this part over here, they knew that because they were setting it with the voltage source. They knew this because they were measuring the drops as they fell, their size, and this is known by everybody, 9.8 meters per second squared. So that means they could solve for this Q, this charge. And what they found was that the charge they calculated was always kind of multiples of the same number. So they'd get the charge on one drop was 3.2 times 10 to the negative 19 coulombs. They'd get 4.8 times 10 to the negative 19 coulombs. And they realized that these were all multiples of the same number. They were all multiples of 1.6 times 10 to the negative 19 coulombs. And so it was determined using that experiment, the charge on a single electron was 1.6 times 10 to the negative 19 coulombs. Now you could ask, how did they know it wasn't 0.8 times 10 to the negative 19? How did they know that this wasn't multiple electrons? Well, they never saw any measurements that were below 1.6 times 10 to the negative 19. Okay, so it must have been that was the very lowest possibility.